Today we will be making an attempt on HackTheBox's support machine. Not the support team at HackTheBox, I'm sure they've got enough to deal with, but the actual hackable machine called support. This is an easy box with a 4.5-star rating, which is pretty untypically high for this type of box. It has quite a few user owns, but a fairly sharp drop-off into system owns, which means we may need to summon some ingenuity to finish this off. As you can see, this box is a Windows box, which is also in and of itself somewhat unusual for the easier levels. You can also see from the user rating graph that it seems to be on the medium side in practice. So let's go ahead and start things off by loading up our Kali VM. I'm using Virt Manager, which is a fairly feature-complete, free and open source VM for Linux machines. Once we're in, we're going to start the way we usually do, with a ping sanity check, and it looks like we can talk to the box just fine. We're going to follow that up with an nmap scan of the top 3,000 open ports of the machine. True to its nature as a Windows machine, there's quite a bit of noise running on this box, so if you scan fewer than the top 3,000 ports, there's actually a good chance that we'll miss something. Quick aside, I really dislike nmap's argument naming scheme. The -pn flag allows us to scan a machine that doesn't respond to nmap's uptime probes. But what does that even stand for? Ping no? The SV flag allows us to do banner grabs to ID some of the services running on those ports. But is it supposed to stand for service verbose? Anyways, as it turns out, this machine is a great exercise in training yourself to exhaustively enumerate and research each and every service running on the machine to make sure that you understand the environment, as we'll be using almost every service running for our exploitation. Let's go over each of these, although there's actually fewer services running than it may appear due to multiple ports being used for single services. For example, DNS appears to be running on port 53, but Kerberos takes up both port 88 and 464. I don't have all year to describe the Kerberos specification in detail, but it's essentially acting as a single sign-on authentication service for almost everything here. For instance, on ports 135 and 593 is the Microsoft Remote Procedure Call service, and in order to use it, you would generally authenticate with Kerberos first. That said, I don't really understand what it's for or if it's exploitable, so go read the Hacktricks book page about it if you need help falling asleep tonight. Ports 139 and 445 are both related to an SMB service, also referred to as Samba, with 139 acting as the NetBIOS version for compatibility. This service is also most likely using Kerberos for authentication, and the main functionality is usually just access to network drives with files on them. Ports 389, 636, 3268, and 3269 are all related to LDAP, which is horrifically old and complicated and makes up the data backbone of most Active Directory environments. In one sentence, it's basically a hierarchical tree data store where each node is itself a key value store and is used to model and store data about corporate structure. It will contain information about the machines, users, and groups within an organization, as well as their relationships, so it will be a high-value target for any attacker. And yes, it will probably use Kerberos for authentication. Last but not least, we see something called WSMan running on port 5985. This is actually a SOAP API running over HTTP to access the Windows management interface, which is apparently different from any of the other things we've already talked about. This can be used for a lot of complicated things that I don't pretend to understand, but one of those features is invoking an arbitrary command on the host machine. So basically, we can treat this service like SSH, letting us use the shell on the host if we have a valid username and password. Oh, and a quick disclaimer. I barely know anything about any of these services, and all my prose is informed by Google and Hacktricks. So if you're a Windows AD admin, you should probably just plug your ears for this one. What I do know is that at a high level, this port scan tells me that this server is probably acting as an Active Directory domain controller. Really, the only reason I believe this is the case is because this is a very typical set of services for a domain controller. So now that we know what's running, there's actually 1,000,001 different well-known exploits on unpatched Windows services that can result in remote code execution. For example, the notorious Eternal Blue exploit gives you system-level remote code execution via the SMB service, which happens to be running on this machine. In a practical engagement, It would not be a bad idea to scan for those with Metasploit, since if the service is vulnerable, it's basically a point-and-click shell. In the HackTheBox environment, even on the easy machines, these types of well-known exploits are usually patched out, as they tend to prefer to test you on novel intrusions that take advantage of misconfigurations. For the record, I did try most of these off camera, but let's assume we know that won't work. What's our next steps? SMB is a good place to enumerate further, since you can usually list the available shares without credentials. We can then use the SMB client with the -L flag to list the shares. This displays the shares, but it doesn't clarify which ones you might have access to as an unauthenticated user. You can actually sit here and try to connect to each one with SMB client and see which ones give you access denied, but there's another tool that will answer this for us more quickly. You can use SMB map to list the same shares, although you'll need to indicate the anonymous user explicitly. This time, you can see which ones are public and which ones are private. This makes it obvious that we should try connecting to the support tools share, although it's worth mentioning that if you're familiar with Windows SMB, you might have already noticed this share since it's the only one that's not there by default. In other words, the machine creator has explicitly created this share for some reason, so it's probably worth checking out. We can connect anonymously to the share using SMB client and list the files within this directory. True to its name, it does seem to contain support tools. Much like with the SMB shares, there are multiple ways that we can determine which of these files may be of interest to us. The first technique you can apply is by simply going down this list and noticing that, well, for example, 7-zip is a well-known archive program, NPP is Notepad++, which is a text editor, and so on. Each of these seem to be well-known, publicly available tools, with the exception of userinfo.exe. If you aren't convinced, you can also look at the access time, where userinfo.exe is also an outlier. So at the very least, it will be worth downloading this file to take a closer look at it. We can do this using the mget command, which will download the file to our attacking machine. Now normally, with a binary that we want to learn more about, we would need to reverse engineer it. I load up the binary in Cutter, which uses Radar2 as the backend disassembler, and while Cutter does reveal some helpful strings within the binary, and especially a suspicious one called getPassword, when I actually look at the disassembly, Cutter pukes and has no idea what it's looking at. We can try to use Ghidra instead, which may have better luck with it, but when we load it up, Ghidra may be able to show us the function table, but it refuses to disassemble the functions themselves. We do, however, get a good hint from Ghidra that this binary is in fact a .NET executable written in C# rather than a native binary written as C or C++. This is actually good news for us as untalented reverse engineers because C# is much like Java, and that it is comparatively much easier to decompile than a native binary. There is a specialized tool that we can use to do this called ILSpy, which I already have installed on my Kali instance. ILSpy is able to show us a fairly representative version of the original source code. At a high level, I'm able to tell that this program performs some kind of query against the LDAP service using some credentials that appear to be baked into the binary. In this case, it's authenticating against the support domain as the user called LDAP with a password that goes through some kind of obfuscation function. Fortunately, this function does not appear to be difficult to reverse, and we can simply mimic the steps being performed in this function to get the unencrypted password that's actually being submitted to LDAP. I could write a simple script in, for example, Python to mimic these steps, but I'd like to demonstrate that we can also do this using the browser tool CyberChef, which is built for simple situations like this. All we have to do with CyberChef is enter the password into the input section, encrypted, and then mimic the operations being performed in the function one by one. As we can see in the function, it starts with a base64 conversion, which we can add to CyberChef, and then proceeds to apply an XOR operation to each byte, where the value being XORed against is based on bytes from some key. The key in question is the string Armando, and CyberChef can do this exact same operation quite easily. We can also see that each byte is being XORed by the hexadecimal value DF, which we can simply apply as another stage in our CyberChef recipe. The resulting output appears to be garbled nonsense, but in reality this is highly likely to be the actual password, for the simple reason that as opposed to before we had applied these operations, there were many unprintable ASCII values in the output of the string that would have been invalid as characters for the unencrypted password. The fact that there are no longer any invalid unprintable characters in this password means that it is very likely that we successfully decrypted it. One other thing I'll mention is that we didn't have to reverse engineer this function, or for that matter, even reverse engineer the binary at all, in order to see these credentials. We could have just as easily run the binary on a Windows machine and sniffed outgoing traffic to see the unencrypted authentication in transit. We could have also run the binary in a debugger and viewed the unencrypted password in memory with a breakpoint at the end of the password function. The best tool for that job is probably dnspy, which is also a decompiler like ilspy, with the additional feature of debugging C# code while it runs. The problem with dnspy is it only runs on Windows, and I wanted to stick to my Kali VM for this one. ilspy is essentially just a cross-platform rewrite of dnspy. The easiest way to confirm that our newly obtained credentials can be used to authenticate with LDAP is via the command line tool LDAP search. We give it much of the same information used in the binary, such as the location of the domain controller, the domain to connect to, which in this case is support, and the user to authenticate as, which in this case is LDAP. We provide the password, and it proceeds to absolutely blow up my terminal with LDAP information. Trying to parse this LDAP data in our terminal is going to be, as they say, a bad time. So instead, I will switch to a more sophisticated tool, which will save all of the same data, but in a more easily browsable and searchable format. This tool is called LDAP domain dump, and we provide much of the same parameters as we do LDAP search. This will fill a directory on our attacking system with HTML and JSON files. The HTML files contain tables of high-level summary information about the object stored in LDAP. As you can see, we have access to information about the users, machines, and groups on this domain. If you are experienced with Active Directory, you may recognize immediately which objects are not supposed to be here. We can also see the entry for our current user LDAP, but it doesn't appear that the LDAP user has any useful additional permissions. The support user, on the other hand, is another non-built-in user account that has several interesting group memberships. The Remote Management Users Group is a built-in group that allows the users to authenticate with the WinRM service that we noticed running on the domain controller earlier. In other words, if we can get the credentials for the support account, we should be able to use those credentials with the WinRM service to pop a shell on the domain controller. The support user is also a member of the Shared Support Accounts group, which is not a built-in Active Directory group, but it is unclear what additional permissions this group may have. To get a better look at the support user, we need more information than is displayed in this HTML table. We can open up the user's JSON file that LDAP domain dump provided and search for the support user in order to see all of the key value pairs assigned to this object. One of these values stands out because it resembles a passphrase and does not seem like information relevant to the Active Directory configuration of this user. In other words, this value looks manually added to this LDAP object. With a name like info, it's extremely unclear what this value is meant to represent. But if you're anything like me, your heart may already be sinking at the thought that this may, in fact, be the password to the support user. We can validate these credentials using the same technique of LDAP search by simply swapping out the LDAP user for the support user and the previous password with our new one, and unfortunately it works. Now, because this is the support user, we should be able to use these credentials in conjunction with WinRM to create a shell on the domain controller. The tool that will automate this additional step is called Evil WinRM. We simply pass it the credentials that we have for the support user, and it quickly gives us the shell we want. Now, I have to come clean and say, I think this is total bullshit. There is nothing even remotely practical or realistic about the presence of a plain text password arbitrarily and intentionally placed into the LDAP structure of the support user. This whole attack chain, while clearly intended by the machine author, is analogous to finding like a passphrase in an HTML comment and then successfully using that passphrase to SSH into the server. This is definitely the most contrived and least practical stage of solving this box thus far, and I'm honestly disappointed. Anyways, back to business. We find the user flag in the user.txt file on the desktop of the support user. Also on the desktop of this user, we find a bunch of notorious hacking tools that were probably left by someone else. I wonder if these will be relevant to us. So to begin the process of privilege escalation to system, in general, there are two ways to go about collecting information for our first steps. If we have no idea what we're doing, Then we can run a privilege escalation scanning script such as WinPeas, which will tell us everything that obviously looks like it may contain a privilege escalation vulnerability. But that tool is intended to be run in kind of a generalized context. The other type of enumeration you can do with privilege escalation is to use the information you already have about the context of the system. This isn't just any arbitrary Windows computer. This is a domain controller in an Active Directory setting. This means that we may want to look into enumeration tools specifically designed for Active Directory manipulation. In the Windows/Active Directory world, one such versatile tool is called Bloodhound. The first is an executable called Sharphound, which once executed on a system connected to Active Directory, will dump as much information as it can about the Active Directory configuration to a zip file, which we can then exfiltrate back to our attacking machine. The second half of Bloodhound is Bloodhound itself, which is a program that we run on our attacking machine. It is not an exploitation tool, but rather an analysis tool that will take in the Active Directory data harvested by Sharphound and use complicated graph theory techniques to tell us where the misconfigurations that can be abused may lie. Now, I know what you're thinking, and you're right. Active Directory is so arbitrarily complicated that you need to use a graph database analysis tool to even know where to begin looking. In order to run Bloodhound, we first have to start the graph database that it depends on, which is Neo4j. When you do this for the first time, you'll most likely have to visit Neo4j in your browser to change the default credentials before you can use it with Bloodhound. For security reasons, I changed the default login from username Neo4j, password Neo4j, to username Neo4j, password Kali. Once we've connected Bloodhound to the database, we drag and drop our exfiltrated Active Directory data, and once it's loaded into the graph database, we can then perform queries against it. I know literally nothing about graph databases, so the most useful part of this application to me is the Analysis tab, which will automatically generate useful queries for finding exploitation paths. The section labeled Dangerous Privileges will tell you if there are any outright problematic privileges granted, but in our relatively small Active Directory simulation, there isn't anything notable returned. The shortest path section of Bloodhound contains some particularly useful queries, such as shortest path to unconstrained delegation resources. When I search this, I immediately get a result, but it is not immediately obvious to me what unconstrained delegation means. Fortunately, on the Encyclopedia Britannica, that is the Active Directory pen testing page of the Hack Tricks book, there are a few headings with this name. Essentially, exploits in the family of unconstrained delegation refers to the act of abusing Active Directory as a means of impersonating other users when authenticating to Kerberos. In other words, Bloodhound is telling us that these groups may be able to abuse their access to impersonate any user on the domain controller. The user we would most like to impersonate on the domain controller is, of course, the administrator user. Back on Hack Tricks, one page that seems particularly relevant is resource-based constrained delegation, which makes specific reference to the generic all permission as a means of privilege escalation. This is interesting because if we look back at Bloodhound, one of the things it's telling us is that this shared support accounts group has this generic all permission over the domain controller. And as the support user, we are actually a member of this group. On a more metagame level, since we know the shared support accounts group was explicitly added by the machine creator and is not a built-in group, we can also guess that this was assigned this permission to provide a path of exploitation. This Hack Tricks page contains a complete walkthrough of the attack chain involved in this process, but I'll actually be doing a simplified version that makes use of Kali built-in tools whenever possible. The first step in this exploit is to create a new machine account that we control in Active Directory. This is allowed by default, up to 10 machine accounts per user, and this is also a prerequisite to this particular type of silver ticket attack. In order to make doing this easier, we will use a PowerShell module called PowerMad, which is explicitly designed to aid in this type of exploitation. We simply upload PowerMad to the victim domain controller and import it as a PowerShell module. We will then have access to the new machine account command, which, as the name implies, makes it very easy for us to add the new machine account. After that, we will then use our generic all permission over the domain controller's Active Directory object to tell the domain controller that this new machine account we created is allowed to impersonate other users with respect to the domain controller. We can see that before I execute this command, there are no principals that are allowed to impersonate on the domain controller. But after I execute this command, my new machine account is allowed. From here, we're actually done with the victim machine, and we switch back to Kali. Since we know the credentials of the machine user we just created, we can actually authenticate against Kerberos with those credentials and ask for a ticket that allows us to impersonate the administrator user on the domain controller. This type of ticket is called a silver ticket, and the process of obtaining one of these is actually much more complicated, but the Python package impacket provides a script that heavily automates most of this process. The script impacket-getst provides a simple, easy-to-use CLI to obtain a Kerberos ticket that will allow us to impersonate any user we want on the domain controller when interacting with a service of our choice. The easiest service to convert into code execution is SMB. So when we create the silver ticket, we have to explicitly indicate that we want the ticket to authenticate us for the SMB service, which we do with the CIFS portion of the command syntax. Once we obtain the silver ticket, we follow the instructions to add the silver ticket to our local Kerberos cache. This ticket will then be used by any program on our computer that wants to authenticate to a service via Kerberos. To turn this administrator ticket into administrator remote code execution, Impacket provides another tool called WMI-exec, which uses the SMB access granted by the ticket and converts it into code execution for us. Once the administrator shell appears, we can read the root.txt flag and the box is hacked.